Okay, folks, let's go ahead and let's get started. I've been getting some pretty good feedback on the lengths of the videos that by keeping it at about 20 minutes, it fits into our 40-minute period. And so I'm going to go ahead and continue on with these, try to keep it at 20 minutes, try to present to you enough information during that time period so that we continue to move forward with the material. But also give you enough time so you can work out the problems and be able to submit the work as well before the end of the period. So like I said, please continue to give me the feedback. That way, then I can go ahead and make adjustments as necessary. But it seems like as of yesterday, most of you were able to get the work in on time. And like I said, I've gotten feedback not only from your class but from other classes as well. The 20 minutes that I spend presenting the material to you is a good amount of time to also leave you some time to get the work done that I ask you to do, the practice work that you have there. Okay. All right. No new word yet on the AP exam, but like I told you, as soon as I learn anything new, I'll go ahead and share that with you as well. Okay. So let's hope. As of right now, like I said, I think the way the format of the exam is going to be set up, it's going to be online. It's going to be a free response and only free response, so no multiple choice section you have to worry about. But outside of that, I'm not quite sure what else they're going to be doing to, for example, proctor the exam and how they will manage the time. And so as I get more information, I'll pass it on to you. Okay. All right, so let's go ahead. Let's pick up where we left off with yesterday. We talked about then, we finished up with the discussion of ionic bonds, ionic compounds, how we can determine the energies of ionic bonds. And we saw then that when ionic bonds form, they may start out unfavorable. That means that energy has to be put in, in order to form these ionic bonds, energy has to be put in. You saw that most of the energies, initially at that time, they were endothermic in nature. That means then energy has to be put in. But the last few energies we saw then electron affinity, and we saw then the lattice energy itself was able to drop that energy way back down so that we ended up with an exothermic process. And so for that bond to form, there has to be an exothermic process. The overall energy for the formation of that ionic bond has to be negative. And make sure you understand the last part of what we talked about there was that there isn't truly an ionic bond that exists between two separate atoms. There are ionic interactions between many cations and anions in that ionic solid, and that's what makes the ionic compound so stable, and thus very high melting points and very high boiling points. But the idea behind that present ionic character is that I wanted to present to you and get you to see then that there are no truly ionic bonds between two separate atoms. And so therefore, from there on, we segued into our discussion of molecules and molecular interactions, covalent interactions, and we saw them with covalent interactions. You can either have nonpolar or polar. We learned that early on in this particular chapter. And so what we were able to do now, and what I wanted us to do yesterday, is that we were able then to describe the bond energies between two atoms in a covalent bond. And so these bond energies we saw then was dependent upon the environment that the bonds find themselves in. And when we talk about environments, we're talking about the other atoms that are connected together within a single molecule. And so that affects the bond energy. And we have differences in bond energy. Even though we have the same type of bond, there will be differences in bond energy depending on the environment that the bond finds itself in. So we saw yesterday with methane. Methane is 4 carbon-hydrogen bonds, but even though they are all carbon-hydrogen bonds, each carbon-hydrogen single bond had a separate bond energy because of the environment that we find it in. Okay? And so what we do then is when we talk about bond energies, or when we reference bond energies, we are referencing actually the average bond energy of the bonds between those two nonmetal atoms, between the covalent bonds. Okay? All right. So we saw then also there was a relationship between bond energy and bond length that we saw then as the bond length decrease, which means then we go from single, double to triple, with the single bond being the longest and the triple bond being the shortest. We also saw then that there was an inverse relationship between that, so that when the bond length decreases, the bond energy increases. So therefore, the single bond had the smallest bond energy, but the triple bond had the largest bond energy. And these again were average bond energies. Okay? All right, so what are we doing? What are we going to do with all these energies? Well, make sure you understand, just like with the ionic compound, a covalent compound will form if and only if, when the atoms get together, the overall energy that is it has to be given off. So if there's going to be, the overall energy has to drop. So the atoms, when they interact, they will should end up at a lower energy state than when they started out with as separate atoms. So we can calculate for that bond energy. We can calculate for the energy that either given off or absorbed when two atoms get together, sharing their electrons to form a covalent bond. So when the covalent bond forms, just like with the ionic bond, when the covalent bond forms, energy has to be given off. And if energy is not given off, the bond doesn't form. And so we can calculate, we can determine that bond energy using this very simple formula down here, which is what we had. Okay? So delta H here then, this is the enthalpy. Remember delta H, and H is always the enthalpy, delta meaning change in enthalpy that occurs when a reaction occurs to form a new product. Okay, so what we're dealing with here then is reactant going to product, a general version of a reaction. So the compounds, the substances in the reactants here, those bonds have to be broken in order for these new bonds to form. Just think back to what Dalton proposed in his atomic theory. So these atoms here, they have to break their bonds. Then those same atoms have to go about and form new bonds with different atoms. And so we get the product here. Okay. So if this is a reaction involving molecules, covalent compounds, we can calculate for it. We can calculate for whether this reaction will occur or not, because this reaction will occur if delta H is going to be negative. And when I say occur, we're talking about occurring spontaneously, which is what we will talk about when we get to the thermodynamics chapter, when we get to the thermal chemistry chapter. So we can calculate, we can determine then whether a reaction will be spontaneous or not spontaneous, which means then it will either give off energy here, that's exothermic, or it has to absorb energy for it to go. Okay. All right. So calculating for this, then we're going to take advantage of the bond energies to form this very simple sigma here. Capital sigma just means that we sum up all the bond energies of the reactants. Okay, and these have to be broken. And remember, the average bond energies that are given to us on the table that I presented to you a couple slides back, all those bond energies are positive. Why? Because those are the energies needed to break the bonds. Okay, so we can get these numbers right here directly from the table. Okay. N here then represents the number of moles, so make sure you keep that in mind. That's the moles of each one of those particular substances in the reactants. And then same thing here, we take all of the bond energies of the products. Okay, this is the moles, and this negative sign right here, will determine then, tells us then that the bonds here are broken. Positive sign here, bonds are bonds are formed, and positive sign here, bonds are broken. So we have to input energy to break the bonds, and then as the bonds form, they give off energy. And that's what this negative sign here is. So make sure you remember that it's a negative sign. Okay? All right, so we worked out this problem yesterday, and I worked it out for you, and I asked you to finish up with this particular problem here. And so I want to work out this problem with you. Okay? So if you notice here, the reaction, they're asking us to find then delta H for this reaction. Okay, so what is the enthalpy for this reaction here? So the enthalpy, the heat of the reaction. Okay. All right. And so if you take a look at what we have here, okay, it looks like then what happens is that the triple bond here, okay, goes from the nitrogen to carbon, and it stays with the nitrogen carbon, but it looks like these two switch places. So you got to be careful about that. And let's take a look at what actually happens in this particular reaction. Okay, so these are the bond energies that are given to you. We find these bond energies, and remember, these are all positive values. These are all positive because this is the amount of energy needed to break these bonds here. Okay. All right, so let's go ahead and let's examine what we have here. Let's take a look at what we're going to do in order to solve for this. Okay. So I'm going to draw the structures out here for you and make sure you are able to do this as well. We'll do more of this in just a moment when we get started with the Lewis dot structure. But carbon here is going to be the center atom. It's going to be connected to 3 hydrogens. So that's what we have here. This is what we call the methyl group in organic chemistry. And this carbon here is attached to a nitrogen by a single bond. Okay? And then this nitrogen here is attached to another carbon, a triple bond. And then we have a okay, so there is where we have then our first structure. Okay, that goes then to the second structure. Let's go ahead and draw and see what happens there. Okay, so first of all, then what's going to happen is that the methyl group stays the same. We have then 3 hydrogens attached to the carbon. This time, though, what you notice is that this methyl group here is attached to a carbon here. So the carbon, so whatever happens to there's a rearrangement where this lone pair here forms a single bond with the carbon, and basically we flip this around. Okay? That happens in organic chemistry. For those of you folks who are moving on, you're going to see that these reactions do happen. And so we have then this compound here. So I'm going to go ahead and erase that. Okay? So that is the essential, that's essentially what happens. What essentially happens is a new bond does form. But this new bond then is a bond between, if you notice here, what has to happen, let's go and trace to see what happens here. You recognize this bond has to break. It's a carbon-nitrogen bond that has to break, and it's this new bond here that has to form. Okay, so the triple bond does not change. And so the amount of energy needed to break the carbon-nitrogen bond here from the previous example, from the previous slide, the bond energy here is going to be 305 kilojoules per mole. Okay, and the bond energy of the single, the carbon-carbon single bond is 347 kilojoules per mole. So to get this problem done, you have to be able to draw these structures. Again, we'll get to that hopefully in just a moment when we talk about Lewis dot structures. Okay, so let's go ahead and let's write out what we have here. Okay, so let's go ahead and write down the formula. The enthalpy for this reaction then is going to be the sum of all of the bond energies for the reactants. And let's go ahead and write that down. And so this is going to be the bond energy, the bonds for the reactants, okay, minus the sum of all of the bonds for the products. Okay, all right, so let's go ahead and write this down then. So none of these are being broken. So we don't have to worry about adding in any of these energies because, again, they all stay the same. The only bond we're looking at is the single bond, carbon-carbon single bond here, the carbon-nitrogen single bond there. So let's go ahead then. It's a 1-to-1 mole ratio. So therefore, then it's going to be 1 times the bond. This bond has to break. So that's going to be 305 kilojoules per mole. Okay, and we can subtract that from all of the products, okay? And the bond energy, now remember, this is the bond energy for carbon-carbon, so don't make this a negative yet. This right here tells us that the bond's gonna break, so don't add a negative here, or else you do that, your numbers will all be off, okay? And so therefore, then it's gonna be 347 kilojoules per mole. Okay? All right, so we go ahead and do that, and we find then that the energy here is gonna be negative 42 kilojoules per mole, which means then when this reaction occurs, then the reaction here is basically the carbon-nitrogen bond forming and the carbon-carbon bond, the carbon-nitrogen bond breaking and the carbon-carbon bond forming. That is an exothermic process that is negative 42 kilojoules per mole in energy. Okay, so it gives off that much. So, all right, so please make sure you write that down and then keep it to help you understand how this works and the study for it. Okay, so I would like you to try then number 7 here. Okay, so it looks fairly daunting, folks. Try your best with this. Take what I would like you to do then is at least identify the bonds that are being broken and the bonds that are forming. Okay, and then use the bond energies. Okay? Use the bond energies, and then go ahead and set up the bond energies that are involved in the bonds that are being broken and bonds that are being formed. So what you need to do here is you have to identify the bonds that are being broken, bonds that are being formed. Okay, so take about 2 or 3 minutes, okay, to go ahead and do at least that, and then I'll work it out with you. Okay. Okay. Let's go ahead and take a look at what happens here. So let's draw out the structure. So you have a carbon, you have a methane group here. So this is methane. And I would suggest you really draw these out here to help you see what's going on here. Okay, so you have chlorine here, and you have 2 of these, so make sure you don't forget that. Chlorine, chlorine single bond, and then you have then 2 fluorine, fluorine bonds. That's on the reactant side. Okay, So again, we have to identify the bonds being broken and the bonds that are forming. On the right-hand side, we have this molecule here. This molecule here then is going to be a carbon in the middle, connected to 2 chlorines and 2 fluorines. That's what the molecule, that's what the formula here tells us. Okay? And then we have 2 hydrogen and fluorines and 2 hydrogen and chlorine. Okay? All right, so let's go ahead and do this here. We have carbon hydrogen single bond here. The carbon hydrogen single bond has a bond energy of 413 kilojoules per mole. Okay. The chlorine bond here has a, and I'll just write it here, has a bond energy of 239 kilojoules per mole. And the fluorine bond has a bond energy of 154 kilojoules per mole. Okay, so this is all of the bond energies associated with the bonds on the reactant side. Let's go ahead and do the same thing for the product side here. So for this particular molecule, we have a carbon chlorine bond, and we also have a carbon fluorine bond. Bond energies for carbon chlorine is going to be 339 kilojoules per mole. Okay. The carbon fluorine bond here is 485 kilojoules per mole. Okay. And again, all these numbers are taken from the table. So table 8.4, you're going to take a look at that. Okay. Hydrogen fluorine, this bond here has a bond energy associated with the 565 kilojoules per mole. Okay. And then we have the hydrogen chlorine bond here. It has a bond energy of 427 kilojoules per mole. Okay. So what I've done here then, I have identified the bonds and looked up the bond energy. Okay. Identified the bond between the 2 atoms and found the bond energy. Identified the bond between the 2 atoms here and identified the bond energy here. Same thing with this here. We have 2 different bonds because you have two different types of interactions. You have a carbon chlorine interaction. The bond energy there is 339 kilojoules per mole, and the carbon fluorine interaction here, which has a bond energy 485 kilojoules per mole. This is hydrogen fluorine, hydrogen chlorine, and these are the bond energies associated with them. Okay. All right. So now, with that said, then we have to make sure that we account for the total number of bonds that are being broken. So going back here, if you notice that all of these bonds have to break, all 4 of these bonds have to break in order for carbon to form these new bonds here. So therefore, and I'll put this in red to make sure you remember then, therefore we have to take this bond energy and multiply it by 4, because there's 4 of them. 4 of these bonds have to form. Okay. Here, 2 of these bonds have to form. Why? Because we have 2 of the chlorine molecules here that are part of this balanced reaction. Okay, so 2 chlorine molecules are part of this. So 2 bonds have to break there. Okay, and so we're going to multiply that by 2. And so we'll do the same thing here with fluorine. Multiply that by 2 because 2 of those molecules have to break. Okay. Now on this side here, 2 carbon chlorine bonds have to form. So we're going to multiply this by 2. And 2 carbon fluorine bonds have to form, so we're going to multiply this by 2. Okay? And from the balance equation, we see that 2 hydrogen fluorine bonds form, so we're going to have to multiply that number by 2 and this number by 2. So make sure you understand where all those red numbers come from and what they mean. Okay? All right, so with that said then, what you have to do then is let's go ahead and let's work this out here. Okay? We're going to go ahead then and we need to sum up everything. Okay, so we're going to find the delta H for this reaction. We need to sum up all of the bonds for the reactants that are being broken. Okay. Subtract from that all of the bonds for the products that are being formed. Okay. So I'm going to leave it up to you to add all those up, but these are the numbers that I get for you. And so make sure you confirm this. So when we add up all of the bonds that are being broken on the reactant side, we end up with a value of 2,438 kilojoules per mole. Subtract from that all the bonds from the product side would be 3,632 kilojoules per mole. Okay? And so when you subtract it, so make sure you confirm these numbers here, please. And if you didn't quite get where we didn't see where we get those numbers from, stop by after school today from 3:15 to 4:15, and I'll work this out for you. But when you add these two numbers together, then the energy that you get then is going to be negative 1,194 kilojoules per mole. Okay, that is the enthalpy for that reaction. That means then when that reaction runs, when the old bonds break and the new bonds form, the overall energy is going to be given off, and this is the amount of energy that's going to be given off right there. Okay. All right. So what I'd like you to do is I'll assign you a problem in just a moment. Then please make sure you work out that problem. Give yourself a chance to work it out and practice this. Okay. And then tomorrow, what we're going to do then is we're going to start our discussion of Lewis dot structures. I'll introduce to you the first of the theories that we use, models that we use to describe covalent interactions. And then in chapter 9, I'll introduce you to the second one. So we'll talk about the localized electron model tomorrow, and then we'll talk about the molecular orbital theory and the molecular orbital theory in chapter 9. Okay? All right, so that was 20 minutes. I've gone just a little bit over the 20 minutes then. Please preview the section 8.8 where we will talk about, 8.7, where we'll talk about the Lewis dot structure. 8.9, and then also look at section 8.9 where we'll start talking about the localized electron model and the Lewis dot structures. Okay. All right, folks. Good. Let's make sure you get the work done, and then please make sure you submit. Okay? And I will see you tomorrow.